Good morning, everyone. Welcome to Thermtest's latest webinar titled Validation of Thermal Conductivity and Thermal Diffusivity. I always mess up this word. I apologize. Diffusivity by MP-1 with TPS and MTPS methods. I'm Angela, your host for today's enlightening session. In this webinar, we're set to explore the intricate process of validating thermal measurements using the Thermtest Modified Transient Plane Source, MTPS, sensor. We'll delve deep into the testing of Pyroceram ceramic, a certified material, to understand its thermal conductivity, diffusivity, and specific heat. This session promises to shed light on the potential of the MTPS sensor for future directional thermophysical analysis of polymers and nanocomposites. I'm thrilled to present our esteemed speaker for today, Dr. Jesmer. As project scientist at the University of New Brunswick, Dr. Jesmer's extensive research and expertise in the realm of thermal analysis make him an invaluable voice in today's discussion. We have reserved time at the end of the session for a Q&A segment. So if you have any questions during the webinar, please type them into the Q&A box, which you'll see right down beside the chat there, and Dr. Jesmer will address them at the end during the Q&A portion. Now, without further delay, let's dive into the world of thermal analysis. Over to you, Dr. Jesmer.
Perfect. Okay, can you hear me okay?
Yes, you sound great.
Good, okay, let me pop open this presentation here. Okay, so if everybody can see that, I'll get started. So as was just introduced, we'll be talking about validating thermal properties using two different transient methods, so the transient plane source and the modified transient plane source method on the MP-1 platform. And also at the end of the talk, a little bit of future testing with polymer materials and composites. So a little brief agenda. First, I'm gonna give a little introduction to glass ceramics, which is the Pyroceram we'll be generally talking about, and then a brief introduction to the actual Pyroceram material, and then some background and theory on transient plane source, modified transient plane source, how they work, and then some actual thermal property measurements of the Pyroceram materials. And then finally, at the end, I'm going to talk about a polymer material that we've been looking at with some anisotropic thermal properties and their measurements. But before that, just a brief introduction to myself and also the group at the University of New Brunswick. So we're a nanocomposite group in the Department of Chemical Engineering at the University of New Brunswick, led by Dr. Philippe Chabonte, who is the Richard Curry Chair in Nanotechnology. And the group has a few different research projects or areas all around the application of nanotechnology, as the name would suggest, for thermal management, energy management, for tactile electronics and piezoresistive materials, and then also kind of a general overall materials science view of production of mostly carbon-based nanomaterials and their applications. So to support all of those research projects, we also have thermomechanical analysis capabilities, which this project that I'm going to be talking about sort of fits into. And to support those other research projects, we have these thermal methods like the MP-1 and the transient methods, and then some other more typical materials chemistry, such as dynamic mechanical analysis, thermogravimetric analysis, DSC, FTIR, stuff like that. So that is the lab itself and what we can do. And then to get started on the actual content, the first thing I want to do is give a brief background on glass ceramics, which is the material that we're using and why we want to use this type of material to validate specifically thermal properties with the transient plane source before going on to experimental materials. So glass ceramics are a class of material that are produced through controlled crystallization of an inorganic glass. And they have a residual glassy phase, and then they have also crystalline phases embedded within that amorphous glassy phase. So these polycrystalline phases have different sizes and different quantities within the material. And that's what determines the overall properties of the glass ceramic itself. So you have anywhere between 0.5% and 99.5% essentially ceramic content as these small islands within the amorphous glass, as shown over on the right side in the little diagram. So starting at an amorphous glass, then you go all the way on the other end of the spectrum, you have a ceramic, which is close packed crystals. And then in the middle, you have the glass ceramic. And the size of those crystals determines like the optical properties. If they're below or above the wavelength of light that they're interacting with, they'll be opaque or transparent. And these properties produce a really tough and heat-resistant material that has low thermal expansion, which is important for what we're doing. And I'll talk about on the next slide a little bit more. And also, importantly, zero porosity. So these are what are known as dense solids. So there's not going to be any convection or radiation happening within these materials in those voids that might be present in a porous material. So they're useful for characterizing thermal properties of the actual instrument themselves. So the specific example of a glass ceramic that we're using today is called Pyroceram, and the specific one is Pyroceram 9606. This was one of the first glass ceramic produced in the early 1950s by Corning. Published on by the late 1950s after they'd published many patents on the Pyroceram glass ceramic. The kind of background of Pyroceram is that it was produced through kind of a accident in the lab, I guess, where the temperature of the oven was set too high to 900 degrees instead of 600. And through that controlled heating and cooling of the glass produced this polycrystalline material that ended up being very useful and marketed as Pyroceram. So Pyroceram was used for a long time as kind of an ad hoc thermal material for testing thermal properties or thermal instruments. And then it has more recently become a certified material that you can buy specific reference materials of Pyroceram. And there's a nice 2010 paper where a consortia of labs all over the world all measured the same samples of Pyroceram from the same batch with a whole host of different methods to determine the accepted values of thermal conductivity and diffusivity in the material. And later on in the talk, we're going to be comparing our measured values to those. And then finally, it also has low thermal expansion, which is nice because it doesn't change shape or size while you're measuring it. So the volumetric heat capacity doesn't change other than the actual intrinsic heat capacity. And the applications of Pyroceram, or you've probably encountered it already in your life, are in cookware, bearing materials, hot plates, stovetops, anything that has to have differential material temperatures. And that low thermal expansion makes it so it doesn't break. So to move on to the actual method that we'll be using. So we're using the transient plane source method to make these measurements. Transient plane source compared to steady state methods has some advantages, such as the test times being quite low, below 80 seconds typically, between 1 and 80 seconds. And you can use really small samples below a couple of inches in diameter. And the transient plane source is an absolute method that measures both conductivity and diffusivity measurements at the exact same time. And something to keep in mind is that you have to, as I mentioned earlier with the porous structures, thermal conduction is the only method of heat conduction that happens, or heat transport that happens for a transient plane source test. So there can't be any convection or radiation that happens. And these little sensors on the bottom left of your screen, you can see is that those are what the transient plane source sensors actually look like. So you take that sensor and put it in between your samples shown on the right side. So you take your double spiral nickel sensor and place it in between two samples and then apply heat. And then you can measure the dissipation of the temperature at the interface. Because we're actually looking at a change in temperature at an interface with respect to time. And then as that temperature changes over time, you can infer properties of the material that you're testing. And the important thing, the entire way that this works is that we have a thin resistive element. So basically just a wire like in a toaster that you apply a current to. And then that nickel spiral acts as both the heat source and as the temperature sensor by measuring the resistance of that spiral through 4 contacts at the bottom of the sensor. And then, as we know the temperature coefficient of resistance of the nickel, we can measure the resistance with time, which is R sub T, and with that find the change in temperature. And knowing the change in temperature over time, we can then find the actual temperature change of the material and its thermal properties. So, as I mentioned, the TPS has several advantages over steady state methods, namely the low test times and infinite sample size are nice because you don't have to put them in an oven if you don't want temperature control. It's also an absolute method, and you can also do isotropic and anisotropic measurements, which we do near the end of this seminar. Some of the limitations are things just to keep in mind when you're doing a transient plane source measurement is that there is a more complex mathematical analysis tied to this type of measurement, but that all happens in the software, so you don't actually have to know how to do that, which is nice. But there are some model assumptions that you should keep in mind while doing transient plane source measurements, and that's namely that your sample is homogeneous. And if it's not homogeneous, you have at least a representative probe depth so that you go through all of your different types of materials. So if you have a nanocomposite, for example, you're going through all of the different particles and different layers. So you're getting a representative sample of your material since you're not actually going through the entire thickness. And some other aspects are making sure that you're applying the correct correction factors. For example, correcting for the probe thickness. There's some papers actually recently that have compared correcting for probe thickness to actually thinning the probe itself by removing the kapton and find similar results for both of those. So as long as you know what correction factors you're adding and what model assumptions are being placed on the calculations you're doing by the software, you'll get good results that are comparable across different samples. And then finally, the 2 different methods that we're using today are the transient plane source over on the left, where you take your sample and place it between 2 identical samples, or your sensor and put it between 2 identical samples. And then on the right side of the screen, you see the modified transient plane source, where your sensor is embedded into a low thermal conductivity backing of known properties. And for that, you can then use it just as a single-sided sensor and use it kind of like a stethoscope, where you just place it right up against your material, your unknown material, and you can determine the thermal properties of it as also an absolute method in this setup. And then finally, just before we get into the actual thermal measurement data that we got, just to give some context of where these numbers lie within the capabilities of transient plane source methods. The general thermal conductivity and diffusivity that you can measure is anywhere between 0.03 and 500 watts per meter Kelvin for thermal conductivity, and put those into perspective of materials you might interact with. Silver or copper, which are very strong thermal conductors, are up to around 300 to 400 watts per meter Kelvin. And down at the bottom of those ranges are something like fiberglass or polymer materials, which are around 0.2. So you can really span most of the thermal conductivities that you might interact with in most materials that you're looking at. And the repeatability and accuracy that we're looking at is within 5% of the actual reported value of thermal conductivity and diffusivity. So for the measurements themselves that were actually done, so we looked at the thermal conductivity of Pyroceram 9606. And these were performed, these 2 measurements were both done at room temperature. And we found a 2% difference between the methods, which is within the accuracy that we're looking for. And also both of those measurements overlapped with the interlaboratory mean by that consortia measurement of Pyroceram 9606 that I mentioned from 2010, which is 4.08 watts per meter Kelvin. And the TPS and MTPS are both repeatable within 1% RSD of their own measurements over time. So the thermal conductivity measurements between the 2 methods are the same and also in line with the expected and accepted values of Pyroceram 9606. And when we looked at the thermal diffusivity that's measured at the same time as the thermal conductivity, we see again that we overlap with the accepted value from that interlaboratory mean of 1.93 square millimeters per second. and both of the methods also overlap with one another, with only a 1% difference between methods, and again below a 2% RSD from measurement to measurement over time. Just something to keep in mind, these methods with the Thermtest software, they're already given with the ITPS for 5 seconds, 300 milliwatts. But so when we did these measurements, we actually used longer test times as well. And you start getting diffusivity and conductivity measurements that are not in line with the interlaboratory mean if you start getting to times where the heat wave actually ends up interacting with the boundary of your material. So when we're talking about keeping in mind the model assumptions, we're basically modeling this as a semi-infinite material that we don't interact with the edges. But when we don't interact with the edges, we're in line with the interlaboratory mean and the accepted values for Pyroceram. So now that we know that everything works and we're finding the same values as the accepted certified material, we're going to look at some polymer materials that have anisotropic thermal values in different directions and compare those, and then look towards doing different types of experimental materials. So the material that we chose to use for this is called Duratron, which is a polyamide imide polymer material from Mitsubishi. And this material has a really high glass transition temperature for a polymer material of around 260 degrees Celsius. And it's prepared by either injection or compression molding by certified molding providers that are certified by Mitsubishi. And when this material is injected or compressed into these molds, the polymer fibers themselves actually align and produce this anisotropic structure. So we would then assume that there will be some thermal anisotropy along those aligned fibers, and then also perpendicular to the alignment, some decrease in thermal conductivity and diffusivity. Duratron in general is a high impact polymer that's used for friction parts that also need low thermal expansion or load bearing materials inside electronics that are going to also increase in temperature as well. So Duratron has a bunch of really interesting applications, and so understanding its thermal properties is important towards actually using it for these advanced materials applications. So we make the anisotropic measurements in essentially an identical way as making the isotropic measurements. So isotropic just means the same in all directions, and anisotropic means different or not the same in all directions. Over in the top left of the slide, you'll see the formula for finding the thermal conductivity, which is lambda down at the bottom, with respect to a delta T over time, with respect to tau, which is the time of the measurement. And when you're doing an isotropic measurement, you're just looking at one single bulk conductivity. But over on the right side, you see that we are looking at two different lambdas that are multiplied by each other in the denominator of the formula. So we're looking at lambda in the XY plane, and then lambda in the Z direction, or in the through plane, or the axial direction. It can be called a few different things. And in this equation, you'll see that the P0 is just the heating power of the sensor and what's happening. And then the alphas are the diffusivity, and the C, the big capital C, is the volumetric heat capacity. And because this is a system of two linear equations, then we have two unknowns, so we can solve it as long as we have a known value of heat capacity. And then the other measurements that we're going to need, or the other assumptions for an anisotropic measurement, are that we're measuring orthogonal to the plane of measurement. So we're looking exactly parallel to the plane sensor, and then also exactly orthogonal or perpendicular to the plane sensor. And we're also assuming that the radial properties in the X direction and the Y direction are the same. So we're looking at anisotropy in two directions and not in all directions of the material. So because we need the volumetric heat capacity to have only two unknowns in this system of equations, for a Duratron, we first measure the heat capacity of the material, also with the MP-1. And so when you're measuring the heat capacity, it changes or it can change with time if you use a too long of a test time. So this is an example over on the left side of 3 different test times to measure the volumetric heat capacity of a Duratron sample of 40 seconds, 80 seconds, and 160 seconds for measurements 1, 2, 3, 4, 5, 6, and 7, 8, 9, respectively. And you can see that up to 80 seconds, we have pretty good and tight measurements around the mean. And then at 160 seconds, because the temperature starts to reach the outer bath temperature, essentially, we're seeing some more variation in the volumetric heat capacity that we measure. So for the actual measurements of the anisotropic thermal properties, we'll use 40 and 80 second volumetric heat capacities that we measure. And so when we plug those into the equation and we solve for both anisotropic axial and anisotropic radial thermal conductivity, we find significantly different values than the bulk value. So the bulk value is the open circles that's in the middle around 0.8 watts per meter Kelvin. And then we see in the through axis a significantly lower value of around 0.4 increasing to around 0.5 with temperature. And then in the radial direction, we see a conductivity of 1.6-ish, decreasing to around 1.4 with temperature as well. So we see that even though there's very little difference in bulk thermal conductivity up to 100 degrees, we do see significant changes in the 2 different anisotropic thermal conductivities with temperature, both seemingly converging around the glass transition temperature of the material. So in conclusion, we used the TPS and the MTPS sensors to measure Pyroceram thermal conductivities, which is a known reference material. And they were within 2% of each other and also within 2% of the accepted values. And within the actual consortia paper from 2010, all of the methods were between 2.7% of one another. So we were well within the accepted values that would be expected. And we also found that Duratron has strong and temperature-dependent anisotropy, which was really interesting. And the temperature dependence was not so expected necessarily. So going forward, looking into the actual control of that temperature dependence and the underlying causes of that could be interesting. And then hopefully in the coming months, using these methods to measure nanocomposite materials now that we have good baseline measurements using the MP-1 and the collection of sensors that we have here. So that is everything that I have for the scripted portion of the seminar. But we can go to the Q&A. If anybody has any questions, I'd be happy to answer anything that you have to say.
I think that was wonderful, and I guess no one can think of any questions right now. You know what? They can always email us if they think of any later on. It's a lot to process and kind of understand, right?
I don't know if my email's in here as well, but it's A and then my last name at unb.ca. So any direct questions as well are totally fine with me.
Excellent. Thank you all for joining us today in today's insightful webinar on the validation of thermal conductivity and thermal again, I always mess up that word, diffusivity by the MP-1 with TPS and MTPS methods. And a very special thank you to you, Dr. Alex Jesmer, for sharing all of your expertise and taking the time to participate in this webinar with us. We very much appreciate you taking time out of your busy schedule. But I want to let everyone know, stay tuned to your inbox. We'll be dispatching a recording of this webinar in the coming days. And I would also like to invite you to join us again on Tuesday, September 5th, with our very own Dale Hume. We'll be giving a webinar entitled Anisotropic Thermal Conductivity, Thermal Diffusivity of Extruded Polymers by MTPS Method. Registration will be open within the next day or two, so please keep an eye out, and we look forward to seeing you at future webinars. We wish everyone a splendid day, and that wraps up today's session. Stay curious and keep exploring.